Okay, so let's start with today's practical session. It will be focusing purely on using a progressively growing GAN model, and it sort of continues on the on some of the content that we had in the last class in the 5th week, the generative models, but I really wanted to focus even on the small details that you sort of need to know to make this model work. And while I think some of the bits are quite easy, or there are multiple ways how to solve those problems, maybe going through that together once here might be helpful for you to get your own sort of data sets working and stuff. So that was the reasoning behind this class. We will start with, or we will go through 3 iPython notebook pages that I prepared, and they sort of correspond to the different steps that you would have when using these models. So I split the training and the inference into 2 different notebooks as sort of compared with the slides from before. So I updated that. All of these notebooks are on our Git repo, and yeah, we will go one by one with them. So I think there is no one correct way how to, for example, do data processing. If you have some other approaches or anything, it's completely fine. This is just like sort of one possible approach to it. Okay, so let's start with the first one. On our webpage or GitHub page, on the 6th week, there are these 3 notebooks. So you can directly start with the first one. I guess one thing to change when you are using them, when you load them up in a Google Colab window, it's important to set the GPU processing in all of them. Okay, so as I was saying, it's important to go into runtime and change runtime type, and then set the GPU here. So with the dataset processing, you don't really have to do it. In the 2nd and 3rd iPython notebook, you actually do. So yeah, we can still start it here. And then let's connect to a machine. So with all of this that we are using here, we are sort of just accessing a Linux machine somewhere on the Google Cloud sphere, where we can just call these commands and sort of use that PC to pre-process some data. It's not necessary to use those. I wanted to have a system which sort of corresponds to something, and that we can all look at it and then try it on our own. Probably something like data processing you would be doing on your own PCs, and so at that moment you would probably even use your own software to change those images or something, or to parse through those images. So yeah, there are multiple ways to do this. Okay, so as I was sort of saying in the last class, and trying to maybe make you also notice that in our homework for this week, creating a dataset and assembling all those images and then processing them is a relatively hard task, especially when it's a dataset which is super large, or if you have had to sort of go one by one with all those images and sort them out or something. So for that not to be that's not the only thing. We sort of have to convert those images into a format which the models that we will be using are compatible with. So Progressive GAN in particular uses a dataset of images on input. These images don't have to be labeled, so it's just a folder of images basically. That's enough. However, these images have to all have the same resolution, and that has to be a multiple of 2. So it has to be 1024 or 512 or 256 by 256, etc. Right? That they can go into lower resolution as well. And they have to have a square format of these images. So it really has to be 1000 by 1000. So I think there might be some edits and hacks of the original repo which will allow you to sort of change that into maybe arbitrary resolution, but I was always working with this one. And there were some sort of hacks and tricks to go around the fact that you sometimes don't have images which would come in square resolution, square format. We are no longer living in a Flexaret. What were the names? Like the old age cameras, 6 by 6 inches, where you were shooting on a film, and everything was square format. So that's the original source of square format, I guess. And then Instagram took it as well. So yeah, if you are sourcing images from Instagram, I guess you would have it prepared already. But if not, then it's a problem. So let's go in this first notebook through some steps which will sort of allow you to process the data so that it fulfills these two rules. Okay, so I will call in a helper function gallery, which will just print out images that we have in some folder, and then then we somehow have to get the data from somewhere onto this machine, onto this virtual machine that's running in the cloud. So there are multiple ways how to do it. One of them would be uploading your video somewhere on your Google Drive and then connecting to that Google Drive and then downloading that video from Google Drive into this virtual machine. And the advantage there is that you can sort of just upload anything. So I prepared a sample here, a video called Big Buck Bunny, which is like a test video for a bunch of things, which we can sort of upload there. So how to do that? We will have to log into the Google Auth. So that will require us to follow these strange things. So basically this connects to your Google Drive. And then from that moment, you can start downloading images or data from any Google Drive folders anywhere. What you have to have is to have the access to those files. So this is a script to sort of download a file with some file ID. And the problem is how to get that ID. So if you share a file from inside your Google Drive, there is some horribly long link usually, and let's write that link down. Some nonsense, and then there is some like string here, which is the ID. So if we copy and paste this ID, just this segment in here, and then we call this, we will download the file, this one file as a file directly into our virtual machine environment. So we downloaded this thing. It has 2 megabytes, so it's correct. And if I check it here, it also has 2 megabytes. So that's exactly the same file. And for 2 megabytes, that's easy, right? You could probably even just use something like uploading the file directly here, and it would work. But let's imagine that you collected 2 gigabytes of images, and by uploading it here every time you run the iPython notebook, it's really painful. So with this command, you could sort of just download it from your own Google Drive, where there is space for like 15 gigs of files. So you can sort of separate all those images there, put them into a huge file, then download them here, maybe unzip them, and then start processing. So that's one way how to do this. I usually use this one, right? Because like your source of video is something that you have processed somewhere else, or this is video in this case, but images or something could also be a source. So that's something that you have processed somewhere else. The other sort of way is to download those files somehow into your own into this virtual machine environment. So basically using a .wget and downloading the files directly from somewhere is enough, because that will download them from internet to this machine. One example of this is the fact that you can sort of get videos from YouTube. So let's install a bunch of things. Okay, we downloaded a YouTube downloader script. We will print out the helper function for it to check if it's working. It is. And list for like a... Okay, so let's see this video. Figuring out dataset sources is tricky, right? But some sources lend themselves to be used quite nicely. So you can imagine a time lapse like this. Oh no, Jesus. Works really nicely as a possible dataset, right? You could have a generative model which maybe generates sky images or shapes, or even like some stuff that you meet on the on a ship. So the advantage here is that it's 10 minutes of video, and so from if you split that video frame by frame, you would probably get a lot of frames in the end. So this is actually a really good source. I am not sure if this particular video is Creative Commons sort of free to use. I don't think so, actually. So this is just a demo, really. But there are some videos which would be CC0 or something, which you could then reuse, cut as frame by frame, process them, and yeah, work with them as videos. So something like a some internet archive sources or something could also work. So yeah, let's call this YouTube downloader. With this command, this will tell us all the possible formats that this downloader can download this video as. I think only the ones with WebM were working nicely. So I chose 247. I chose this resolution because it's like the right resolution in the size. So yeah, let's download that. Let's hope it will work. It's 90 megabytes, but that's easy. Let's so this will just rename it or move the file from this name into just input video name. So yeah, we did that here, and then I would like to process that video. So we can sort of use a just Python code to open up video and have some like statistics about it. So this is running at 30 FPS. It has 18,000 frames, and this is the resolution. So this is enough data for a GAN to be trained on, right? And let's this is just a demo, so I'm sort of not extracting all the possible images from it. I will make a directory called frames, and I will cut or like extract frames from this video at the speed of 1 frame per second. So if this video was 10 minutes or something, it will give us around 600-ish frames, because for every second there should be 1. So let's call this. And yeah, so there are multiple ways how to do this. In theory, you would be getting sources of data from other types of files, right? So you would not be processing a video. You might be uploading directly a file with frames which are already in the right resolution. But if not, this is a sort of setup to help you out. So yeah, all of these steps will take some time, so we can just wait. Something called ffmpeg is a thing that you can sort of run on your PC regardless of the platform you are using. So I think, right? So there will be installation for Linux, Windows, or Mac. So you would end up with something which is running on a command line, and then you could use these commands like this to sort of edit videos. And also, as we will see, also images. Okay, so this finished. Let's print out the directory. And it's a huge directory with a lot of files. So one thing to note here is that we saved everything as JPEGs. And that might not be the best case. So if you change this into PNG, it will save it into a larger, not so compressed file. There are some settings for like for deciding on the quality, so you could still save it to JPEG with some larger quality or something, but this is a demo, so I'm not really showing it. But I think in my own previous processings, video processing, I was just saving it as a PNG, which is much larger, but it will work with the image in its original quality. Because every step that you're sort of saving something as JPEG, you are losing some quality because it's compressing it again and again. So yeah, let's just like ignore that for a bit. Okay, we generated a bunch of images here. If you look at the end of the list, because we have named them all one by one, so it's 600 images, and we can even spoilers. We can look at them. Look at the gallery, use the gallery view, and then look at those initial frames. So as you saw the video, there was a time lapse of some like ship running around, and you can see that some of these first images maybe are something that contains no relevant information. So maybe we don't want completely black images. So with all of these processes, you probably would have to go after processing this dataset and go into the folder and hopefully just check it. So maybe change the start of the video or change the end of the video, sort of delete those files. And this is just 2 files here, but if we sampled it at like 30 FPS or something, it would be 60 files. So yeah, you sort of want to throw out images which would break your model later. Okay, so let's look at one of them with as is zoomed in. So this is looking nicely. If we if we print it out, the shape, well, yeah, this is something that the video was originally in. I think it's the 16:9 sort of standard format. But this is slightly problematic, right? Especially if we want to work with something in the resolution of 1000 by 1000, because the height of this video is slightly less than 1000, and then the width of the video is slightly more than the 1000 that we want. So this is basically not usable in this original form. So there are some ways to go around this. What we will do is basically almost like zero part the image, so add some borders which will change the resolution of the image into having a square format. So that's one edit that we need to do. And the second one is that we will downscale it to convert it into a 1024 by something. So it turns out that if we would like to just resize it, we would go into 1024 by 576 pixels. And of course, this downscaling will be lossy. So you are sort of losing some resolution there, losing some information there. So it would be better if we were working with PNG, but we are still resizing the image down, so we are losing something. But yeah, that's life. 1000 pixels is still high enough resolution for us. Okay, well, so we will downsample it or downscale it into this resolution, which is done with the ffmpeg command, or with this command. But we will also want to pad it around with 2 black stripes. And so if you did this separately, one by one, you would be adding in additional steps where you might be losing some resolution. So I sort of plopped everything into one fast command, and that is using a ffmpeg, inputting one test image, which we just copied one of them as a test image, and then scaled it to a smaller resolution with forcing the original aspect ratio, and then padding that to have this resolution in the end, 1000 by 1000, and with a color black. Okay, and so we will do that. So this is doing this effect on just one image that we chose, this test image. So this test image was in this resolution, and after this operation, we ended with 1000 by 1000 resolution. And if we print it out, well, this is what happened, right? We have added these black borders and also reshaped it to 1000 by 1000. So this is one way of sort of processing the data, so you get a square format. The other possible solution would be to cut a 1000 by 1000 crop from inside this image, but you would be losing the information on the sides. Third way would be trying to sort of search for a progressive GAN implementation which allows you to use non-square formats, but that might be some that might cause some pain later as well. So yeah, that's why I chose this sort of solution, and it's working well. So this the network will sort of learn that there is nothing in here, and it will generate images which have black borders here as well. Okay, yeah. So we are here. We changed this resolution of one single image. This was just to sort of demo this command, right? If you wanted to crop the image, this command would be different, and you can sort of find the exact command for ffmpeg somewhere else. Yeah, it's similar to this, but I think it's a bit simpler than this one because we are adding two operations here. Okay, so we did this edit on just one single image. Let's copy the whole folder of frames into a frames_res, like make a copy of all those files, and then let's go into that folder, and for a one file by one file, we are doing the same edit operation that we did before. So let's run that. This will take a long time, and also I think I didn't write something like silent mode here, so it will just pop out a lot of outputs, which is also good because we know that it's working. And if you want to check more commands, this is my gist from some time ago when I was sort of whenever I was using this sort of edits, I was just writing them down into this. So you might be using something like, yeah, there is something for just padding, there is something for combined resizing and padding. Okay, let's kill it, actually. Stop. Okay. So we killed it somewhere in the middle, so it's not the best because we shouldn't do that, right? In real life, we want to let this continue and finish. But just for now, I wanted to sort of just stop it because we will anyway just load the first few files. Now, if we call this, it will show us the processed images from the dataset, and I mean, like we skipped it somewhere in the middle, so the last roughly 200 will be broken. But if we just ignore that, if we pretend that we finished it, this looks good, right? So if we load one of them, we can check the shape of it and see that, okay, yeah, it's actually running okay. Okay, so this is finishing the first step, the data processing part. In theory, all of these edits could be done with any sort of software on your site, right? So you could do these edits in Photoshop and like create a batch command which would just edit everything, and you might be able to do some more edits or something there as well. Or you could use something like Zoner, which is a freeware software which I have been using every now and then as well to do similar edits or like bunch of files. Or maybe even in Irfan View, you could do something like this. But I got used to sort of doing this with a command line. One advantage of doing it with a command line is that sometimes you will connect to a virtual machine somewhere, and you will not have any access to the actual Windows. You will always be accessing it through a command line. So at that moment, these are the only way to sort of do it. Okay, well, we processed the dataset. Let's pretend we finished the whole folder. And what we would like to do is then take this processed dataset, a bunch of images, and sort of save it somewhere. So we can zip the whole folder of frames res into a dataset zip. And we can download this file. So in theory, you could use this Google Colab .files command or files.download command, but this is working with only like few megabyte sized files. So if you are downloading something which is probably large, I don't know what is the size of this one particular file, but I think it will be a bunch of megabytes. So yeah, 37 megabytes. I'm not sure if this will. I think this might work for 37 megabytes, but for some larger files, it might actually fail. So we will not use this. We will use a better method, which is saving it again into your own sort of drive, Google Drive. So if we start this command, I think there are no errors here. Okay, so at some moment there were a bunch of errors coming or warnings which you should just ignore. This command is prepared to save this dataset.zip file that you had here on the drive. This one, it should save it, or here in the virtual machine, it should save it inside your own drive. So I will, so it will save it into the root of your Google Drive. If you cannot find it, you can just directly search for dataset zip in like the search menu, and it will eventually find it. Okay. And there is 15 gigs of space, so you can usually upload even like 5 gigabyte files using this method, and it will never fail. This is really fast, and so you can also just like start all of these edits, start this processing, even if it's a lot of images, and then sort of click display here, and add and zipping as well. And at the end, it will just automatically fulfill all of those steps. So you don't have to be waiting with this Google Colab window. You have to have it open, but you don't have to be sitting there and clicking it manually. You can just start all of those commands and just wait for it to finish. And at the end, it will just upload it to your drive. And then when this notebook dies, which happens after some time of not using it, it will still remain in your own Google Drive. So in like the in some years when I didn't have any PC to work any magic or any machine learning code on, nothing powerful to sort of process anything, I was using a Google Colab with these sort of commands to sort of process datasets, download them, then load them with another notebook somewhere else, process them again, train something, then save the model, and then use those models later. Everything in Google Colab. It's a bit more tedious, but it's still possible. Okay, and then this is just a spoiler for the next notebook. We will see that in the next one, but this is looking at the at how to load it into Progressive GAN. So I will just don't look at anything here, but what is important here is that we will end up with a line saying something like dataset shape having 3 by 1024 by 1024, and then somewhere here adding 600 images. So these are some things that you should sort of check when you're loading them into the model. But we will see that more in the second notebook. Okay, so right now let's have a pause of like 15 minutes, and we can continue with the second notebook. Let's continue with the second iPython notebook. We will look at training a progressively growing GAN. So one thing to sort of note from our previous class is that the progressively growing GAN is the same as a regular GAN because it has a generator and a discriminator setup. And like there are some tricks in there, but the most important trick they are using is that they are iteratively increasing the resolution of the generated and also the discriminated image. So inside their sort of architecture, they are adding blocks of convolutions and upscaling and downscaling. So where they start with 4x4, they will sort of grow this resolution one multiple of 2 by another multiple of 2. So eventually they will get to a very high resolution, but over the training they will start with something relatively low res as well. So if you look at this at a particular point, we also saw this previously. we will sort of see this process where we are increasing resolution 1 bit by bit and then sort of getting better and better resolution there. And sort of you can also note that this trains relatively slowly. So, and this was even on a quite good machine that they had. So in the demo that I will be showing today, we will not get into being able to train this on our on Colab purely, but I will more or less talk about the way how to set it up and how to run it. Practically speaking, this will then take maybe even like weeks or something of training time. But when you sort of start it, you can then leave it running and return to the PC in like a week or something, and then you will have a model which is working reasonably well. So the limitation here is that we will be showing it on a Colab, Google Colab, but we cannot really train it there because it will just not finish, and there are some memory issues as well. So this will be just a sort of demo of the code. So as I was finishing the dataset processing in the previous notebook, we ended up with saving a zip file, and it will save it on the root. And sometimes that's hard to find because that can be quite messy. So you can just sort of search for the dataset.zip and it will pop that one out. You can either download it directly to your PC and then sort of inspect the frames on your own. And I would recommend you doing that because sometimes you can see that, I don't know, maybe these images are a bit messy, and maybe something at the somewhere in the middle there are some scenes that you might not want, or maybe you want them, but like, yeah, it's good to inspect this manually. Or maybe somewhere at the end there are some like things that you also would like to delete. So you would do this sort of processing, and this is best done on a PC which shows this as a grid, so it's not with these gallery functions that we were sort of working with. Okay, I think we can continue with the second notebook then. It's the one that we can find on the in here, so the to train progressive GAN, and in there we will talk about how to sort of start up a training process of a progressively growing GAN. So in this moment, it's quite important to set the hardware accelerator to GPU. Previously, it was not necessary. In this one, it is, because the model will be using it. And yeah, we will be maybe signing into the Google Drive again and maybe downloading the same data again. But yeah, that's just some redundancy. But mostly, I think we will be just installing the new repo. So we are cloning the progressively growing GAN repository and then going inside it. Then just to sort of check the version of TensorFlow, and maybe also print out the NVIDIA SMI as a proof that we are connected on some GPU machine. So this seems good. We are, and then we will log in the same way to a Google Drive notebook. Or I mean Google Drive from this notebook. Okay, so this one will right now download the network file, which was sort of the pre-trained files that were released with the original paper, and then print out this the folder that we cloned from Git for the progressively growing GAN. Okay, so there is a question in how to process the data there, because the progressively growing GAN code doesn't really work with files of images directly. You have to sort of pre-process them even more. So you have to save them using the dataset tool. So in order to create a dataset, we will have to somehow get the files there. Well, let's prepare some folders. So let's prepare datasets as a folder, and then let's sort of use the dataset tool. So if we are using your own custom data, you would be using this dataset tool. Well, we can actually see what this prints out with no settings. This is a code written by the authors of the Progressively Growing GAN paper, and there are all of these sort of commands that you can use to create a dataset. The reason why they are pre-processing the dataset even more is that they will save it into some format of their own, which is really efficient in terms of accessing the files accessing the files rapidly. Because as you could see in the slides about progressively growing GAN, we are looking at images at various resolutions. So during the training process, we will be sort of scaling and looking at different resolutions of the images. So this step is sort of changing the representation of the data to include all of those resolutions on their own. So we don't have to do anything here. We will just sort of point this script to our own directory. And so for that, we will run this command with create from images command, and then print out the help. And it will tell us, okay, you have to give us the folder where you want the dataset to be saved or created, and then the folder with images. Okay, so let's do a demo of this. So one demo would be just to download like some images from the internet. I downloaded 2 images from somewhere, and another demo would be to actually use the dataset that we just cooked or like prepared. So let's do that. Maybe that's better actually. Let's share this dataset.zip. Get the link and then paste it here, and then this is the ID that we care about. Let's call it correctly, so dataset.zip. And when we are done, let's just print the files. We will have to unzip it, I think. And I forgot the command exactly, so it might fail here now. Okay, it's actually correct. So this was the command, and if I look at the directory, where did we end up? Frames res2, yeah. So this is the folder that we right now downloaded, which is full of 600 images. So this is not with like I didn't download, I didn't delete any of these images there. I would upload a newer version of something that I processed on my PC, so it's updated with that. But yeah, anyway, this is just a demo. So let's create our own demo dataset from this folder of these 600 images, hopefully, and let's call it a demo time-lapse dataset. And so this would be the command to create a its own representation in the datasets folder, in a folder called demo time-lapse dataset from our images that we provided here. So this will work a little bit. Okay, amazing. So it went through the 600 images and then added all of them. So we can look into the folder datasets. So this is the one that we created here, and we can see that it created a folder inside that folder called demo time-lapse dataset. And if you look inside it, there are these TF records files, R02 all the way to R10. And if we print it out with this luach, this is printing it with all the details, we can see that this dataset that we processed, this 36 megabyte file, was sort of unpacked into the original 1000 by 1000 resolution, and then downscaled into half of that, and then half of that, and then half of that. But the problem here is that it sort of works with the files in its raw resolution. So even though we worked with JPEGs, it converted it to something like raw pixel values. So at this moment, this is really huge, and this is not really portable as well. So it's much easier to work with these sort of images separately, and then have this processing done on every machine sort of independently. So we will never want to really move these files, because we want to just directly move this zip file and then have the processing happen on any PC that this is working on. So if you were working on your own local machine, we could just say, oh, not demo dataset, time lapse. I think this will yell at me that it couldn't find it, yeah? It's not a directory because it couldn't find it. We can call display, still using the dataset tool, and in theory, this should give us a window, like a window should pop up with visualization of that image. Because we are on a virtual machine that it doesn't have any sort of Windows setting attached to it, it's just command line, we cannot see it here. But on your own PC, you would be able to see images one by one. Okay, well, so this was the first sort of setup, or the first option, to use your own custom images. If we print out the help for the dataset tool, you can see that there are all sorts of other prepared functions to process different datasets. So something like MNIST, MNIST RGB, CIFAR10, CIFAR100, all of them, LSAN, CELEB A, so these are the faces, CELEB A HQ, so these are faces which are in high resolution. You can call all of these to sort of create the datasets which are already one of the standard ones. The caveat here is that for all of these, you will have to download the files for the dataset on your own, and so it's not super easy sometimes. So the MNIST dataset is relatively small. So if we just run this command to create a folder with MNIST, then download the files from like someone somewhere to run a download MNIST command, then this downloads these images, and then we go up a bit again, and then we can create a new dataset called MNIST from this MNIST download folder. So let's just run it, and you should see that this will run much faster than the processing of 600 images. This should run with all the 60,000 images in the MNIST dataset and create its own sort of representation of the MNIST. So if we will look at ls datasets, so it will again clone MNIST in like 28 by 28 or maybe 32 by 32, and then also a version with 16 by 16, 8 by 8, 4 by 4. So if we look into datasets, we have MNIST here as well, and if we print out what happens in MNIST, this is much smaller, right? Because the highest resolution is something which is manageable. In this case, there was a support for the labels, so we loaded the MNIST dataset with labels as well. So the progressively growing GAN can also work with labels. I was mostly working with unlabeled data with it, because when you are just scraping something from somewhere using images from video, even on your own sort of recording video, so maybe you go out, record 30 minutes of something, and then process them using that previous notebook, you would end up with not labeled data. But it also supports labeled data. Okay, there is one more option of using like a CIFAR10 dataset, so we can run that as well. And then create its own create a folder for the CIFAR. We have to, for that we have to comment some lines in the dataset tool, because there are some checks for like MD5 consistency and then something like this, and maybe because of the different versions of code that we are using, this is no longer true for some reason. I think that the problem will be here with the types of the loaded data, but because maybe it loads in like 64 instead of 32. So yeah, so there are some errors here, but if we were to edit a dataset tool.py, over here, and then find the assert. Can we actually search in it or not? Yeah, it's not allowing us. So we would have to like find the cifr10 here and then comment out these assertions. Then save it. So this allows us to change the code directly. We have seen that this changed into saved file, and then if we rerun this this tool, we will run an edited version of it. So now apparently there are no errors. So something similar happens even if you are working with the Celeb A dataset or the Celeb A HQ. There are some small differences in some checks, so some assertions make no sense anymore. So yeah. Okay. So that's another sort of dataset that we can use. And the final option that I will mention here is that you can download datasets from Kaggle, which is a resource for well, it's a place where there are different competitions, but there are also these Kaggle datasets. There are also all sorts of datasets which can be used in your own projects. And there are some public ones, so you can sort of just search through this and find the ones which would be with images. That might be here, right? Creative Commons, definitely, and image, no? Arts, yes. Okay, I think that's it. Best artworks of all time, 2 gigabytes. It's CSV values, but then also images, and then also resized. So yeah, this is just one example, right? There will be artworks like this, which have been scraped by someone else, probably. Yeah, with a CC license. So this is a cool place to start, for example, with something. So how to download these? You need to have your own account here, and then you would have to use the Kaggle API, which is this link, the official API. There is some setup that you need to go through. So install it is one thing, but then also set up the API credentials. This is a little bit of pain, so I will not go through this. But yeah, it's not too difficult. It's just like a lot of hassle with setting different files somewhere and on correct locations. And then you will export something, and then you will be able to download everything using the Kaggle datasets download. So by using that, you could download a folder full of images here as well, and then you would probably use the Python dataset tool, create custom, right? This one, I think it was custom. Oh no, create from images, point to that new folder that you downloaded from Kaggle, and then you would create a new dataset. All of the problems that are included with all of those datasets are always present, so you will have to sort of check if everything is in the same resolution, if everything is square, etc., etc. Right? This is like endless struggle. So yeah. So we are in the. We won just the first bit, because if we now look into the datasets folder that we created somewhere at the start, we created three datasets. Well, still like pre-processed the data in the compatible format for this network. Cool. Well, this is not enough. We will need to set the code that we just downloaded from the Progressive Growing GAN. We will have to edit it to sort of point to the correct datasets. So for that, we will back up the config.py, because the config.py file is where you will change the commands of which dataset is being loaded. So I don't like I have not figured out an easier way than just changing these config files. There might be some command line changes on a command line which will change the directory as well. But I think it's easiest just to change the stuff in the config.py. So we will look at this, but just briefly, you have to sort of uncomment or comment lines, and these lines mean or correspond to which dataset you are sort of training on. So by default, the celeb AHQ line is is without comments. So this one is the active one, and it will load the files from celeb AHQ folder inside the datasets. We have nothing in the datasets folder, which would be called celeb AQ, so this would fail by default. So we will have to edit it. One sort of additional trick that why I really like Progressively Growing GAN is that using this, changing some things in the config.py, you can resume training of already sort of started network. So you can train this network for 1 week, start from 4x4 resolution, get all the way to maybe 1000 by 1000. But at that moment, it's still relatively rubbish. So you can still resume that training in like 1 more week or something. And you will see that the network is maybe eventually overfitting and maybe doing badly. But you can sort of start somewhere in the middle and sort of continue with that. I think this opens up possibilities for some like hacky stuff of like training it on one dataset and then training it on another dataset and seeing what it does with all of that, basically, if it's able to sort of capture all of the different images from two sources of data. But even by default, like just being able to resume your training is really handy, especially when you're like your PC running somewhere dies for some reasons. You're able to recollect the data, but you still would like to start somewhere with the code. So yeah, that's also a reason why I think I quite like this repository. Okay, let's see, config.py. Okay, let's open it here. So this is slightly messy page with a lot of code, which has all sort of utility scripts inside it, all sort of hacks that they used when training the original network, all sort of presets, but also all sorts of default versions for training the network on some particular dataset. So if we want to create our custom one, we have to comment this, enter a new line, which we can call whatever, basically, but we have to change this tf record directory to the one which we had here. So yeah, so this works. Okay, demo timelapse dataset as the tf record. Let's call it maybe like timelapse or something. And this train mirror augment true will allow it to mirror the images. So if you look at these images, maybe if there wasn't any text, that would be okay, but as there is some text, oh, look at the horrible way of how pixelated this is. I think, yeah, this is because I was working with JPEGs, so it's very low quality. Well, yeah, there is text in there, right? So we would probably not want to mirror this. So let's erase this. Okay, so first setting that we can set is changing this description, so pointing it to the correct directory, maybe changing the mirroring as well. Then we can look here, and then there is a lot of detail there, right? So there are a lot of different setups that you can use. I think there are, if you're using a conditional, right, if you're training a model which is conditioned on the labels, then if you would uncomment this, or this. If you are using a right, you can sort of change the precision of your model. So in theory, this second line should train faster, but maybe it will fail horribly. I think I was testing with something and it was failing horribly, and it was not particularly that much faster anyway. So like some of this you should just keep the same, but some of it you can sort of experiment with. there are some things that are described in the original paper. So no smoothing, no repeat, no leaky relu, no scale, no v-scale, no pixel norm, no growing. All of these tricks are sort of features that they implemented in the paper, but you can turn them off one by one. So the no growing, for example, is the main trick. The fact that you can that the resolution is progressively growing, so you can turn even that off. So probably you will not be touching any of this. You can change the verbosity of it, and I think there are some more debug options here. One thing that you might change or might have to change is this line. So the config presets. If you by any chance have like 2 GPUs machine or 4 GPUs machine or 8 GPUs machines, this code allows you to train on all of them at once. And so there are different commands for that. If you are a regular human and you don't have 8 machines like people at NVIDIA have, then you will probably stay with the original one. Even with this, you can then change some of these settings here. I think, practically speaking, I had to change something like this number down, because this is telling me how many images of that resolution, so of 512, it will take into memory when training at that resolution. And so I think 4 was maybe crashing my PC when I was training some models with it. So I had to change it to some maybe like 2, and then to add a option for maybe training with just one image at once at the same time when training. So this is something that you will figure out on your own, sort of, and then it depends on the hardware you are using. Okay, so I undid that edit. There are other changes that you can check. So how many images it will train on before it goes into the next resolution. And I think there are some descriptions for these as well. So somewhere in the code, all of this is commented and explained. I don't remember where. Shed dot something. So what is this head? Okay, let's save with this edit. I think somewhere in the train.py or maybe some of these other commands, you would be able to check like human descriptions for the options that you are changing. So you can sort of see what you are turning off and or on. But by default, you will not be touching this much. The main edit you will have to do is changing this directory into something that you just uploaded it. Okay, so that's also what I wrote here. Let's print out the debug now. So we have commented the Colab AHQ, and we have added a new line with the demo timelapse dataset. So by default now, this will load this timelapse dataset. So the problem here is that the virtual machine I was trying this on, it failed after like 3 iterations, even with a MNIST. I'm not sure if the virtual machine that I'm currently connected to has a larger memory allowance. I don't think so. There were some tricks that people were saying that if you run this before it will not print out some warnings, but I think it will still kill it. So yeah, on your own PC, you would probably not have these problems. But on the Google Cloud, we can start it and see how it runs, but it will not be able to train anything really well, which is a shame. Okay, so after editing the config.py, we can just call python train.py, and it will load up all the configuration from the config. So we can just really run this and wait for 2 weeks, basically. Or yeah, let's see if it's all correct. So dataset shape 3 1000 1000. This is looking nicely. Dynamic range from 0 to 255. So it means that it's an RGB image from black to white. Label size, we don't have any labels with this dataset. And now we are looking at the generator and the discriminator network. Okay, and here there is, whenever using TensorFlow, there is always a lot of warnings, so just ignore that because they are changing the versions rapidly, and so things get deprecated really fast. So yeah, it's setting some, it's saving these some images. Before that happens, I think I will let it run for a bit, but we can look at this debug. So we created a generator and a discriminator model. So generator is this part and discriminator is this part. Generator goes from a 512 sized latent, which is a value actually that you can change. So you can have it generate latents which are 512 values, or something which is 128 or 1024, whatever. You can change that value somewhere in the config as well. And then it will scale this vector into the original image and then train the generator and the discriminator together to be able to generate faces or the dataset that you gave it. Okay, so this debug here is something that we have basically seen with like the network.summary. Is going from latents from 512 sized vector, then using some various tricks somewhere in the middle as well, but there are fully connected layers and convolutional layers, and upscaling layers somewhere as well, upscale 2D. So this will, I think here there is some upscaling as well happening. Here is an upscaling layer. There are a bunch of convolutions being repeated at various resolutions. So this is 4x4 resolution image with 512 channels, 8x8 resolution image with 512 channels, 16x16, 32x32, and all of this corresponds to these growing resolutions. And as it's written here, it's the maximal network. So we have all of this connected all the way to 1000 by 1000, 1024 by 1024, and then the other part of this network, so not just the generator side, but also the discriminator side, which is then getting these images at that resolution and then slowly downscaling them all the way to a label where we are assigning it either a flag with the image being real or the image being generated. So it's just one value basically. So even though you see everything here, there are some tricks somewhere happening in the background which are basically not allowing this network to be trained fully from start. So at the first iterations, we are just using basically this part of the network. We are using it up to the 2 RGB level of detail 8. So we will pop out these images at the 4x4 resolution, and so this thing will connect to the from RGB level of detail 8, and it will plop it at this moment. So 4x4 with 3 channels, and so it will connect at this moment. And at that moment, this network is really small because it's training just on the 4x4 resolution of the images. Okay, let's see if everything is correct. Well, so it's telling us we made some result directory. We will look at that later. And we are saving the results from this training into the 00 progressively growing GAN time-lapse, which is what we set the name to be, preset using B2 with 1 GPU with 32 precision of floats. All of this is nice. And then there are all of these large alloc errors or like problems, and this is basically telling us that we are running out of the memory. I don't know if it's a CPU memory or if it's like a RAM or if it's a GPU memory. I don't know. What I know is that after like 3 iterations, the code will actually fail on the Colab. I think they will kill it because there is some they will notice that the resolution is or like that it's still requiring a lot of memory allocation. So yeah. So this is really a guide for you to use this network on your own PC probably and leave it running on something of your own. But this is the edits that you would do would be the same as on this Colab notebook. So at this moment we are just training this network, and it will take forever. It will take 2 weeks, maybe 3 weeks on a good PC, and maybe really long on this shitty on my own shitty PC, or really long on this virtual machine as well. If we look at the Progressively Growing GAN repo, this page, there are some some details about this. So this took 1 week to train on 2 GPUs, 2 weeks to train on one really good GPU, actually, Tesla V100, and on something like 8 GPUs, it takes just a few days, so it's fast. There are some different. So this the same author created additional models which are training slightly faster. But yeah, it's just with 1000 by 1000 resolution images, it's live. It takes a long time to train, and none of us has 8 GPUs. So yeah. Okay, I will leave this running and just go through the rest of this notebook. The reason why it's okay is because we will be using some already trained models later. So yeah, we are not depending on what we will train here. So if we print out the results folder, I was previously playing around with a MNIST dataset, so there will be some just sort of result folders from for each of those datasets. So it will be called whatever it was telling you that the result will be as, so this thing. And it will save the a debug version of the config, so telling you what you started the network with. It will save a reals.png file, which is usually quite large. This will contain basically images of the resulting dataset. So this is the real images, and then every iteration it will save these fakes 00000 and then 00001 and then continuing, right? So this will at start it will just have noise with it. So let's see if it even loads. Yeah, so this is what this produces with a network which is completely empty at the start, which is actually quite nice because it's producing some artifacts which kind of come from the convolutions, but all of this is just random numbers. So it's producing random noise, but which actually looks quite nice. But yeah, at this moment, we have learned nothing yet. And because this is relatively slow, it will still take some time before we create the fakes 0001 or something. So previously, when I was running it with a MNIST, you could then load up the sort of look up at the gallery of that folder, and you can then particularly look at like each one image from that, and so you would get something like this. This was a MNIST dataset where this is a grid of bunch of samples, and we are I think we are trying to generate numbers from there, and so these would be 2 by 2 pixel sized generations, I think. Maybe it's 4 by 4 already, I don't know, but it's nonsense here, right? But over time we will get better and better results. Yeah, it's still not printing anything out. Well, so what we will sort of end up having is, if you play this video again at the timestamp, we will be generating frame by frame these images that we are sort of creating here now, right? So this is just a video where they placed all of those images one by one after each other, and you can sort of look at the progress of the training. Okay, so I will leave this running. I don't know if it will get to anywhere. If there is another result, I will sort of show it to show you the basics output that we would get after like the first iteration. Practically speaking, now is the time to sort of leave the PC, go for a vacation, and then return after a week to discover what it trained on. So the advantage is also that over this training time, it will save these outputs, these debugs, but it will also save some intermediate versions of the network. So it actually produces loads of files which take a lot of space, but the advantage is that you can sort of look at various networks at various points of their training progress. So the first ones that we will get here will be probably rubbish, but the later ones will be better and better. And at some moment you could also just overtrain the network. So it's really good to, or it's really handy to have some previous versions of that network saved as well. Okay, so with this, I will leave this notebook running to see if anything gets finished. I'm not sure if it will be, but let's see. And we will then continue with this third notebook of working with an existing progressively growing GAN, so pre-trained model, and then looking at what we can generate with that. So let's continue where we ended. I was checking the outputs of the trained of the training. After all that time, we were able to sort of just have just one of these ticks. So this means that it parsed through 160 thousands of images. So we have 600 images in the dataset, right? So it went through those again and again, multiplied them somehow, and then I don't think that they used any augmentation there. It was just sort of repeating those images again and again. So eventually this GAN will fail because we have very small dataset for it, but still it went through 160,000 iterations of looking at images, and that was in 18 minutes. So the later iterations will take more and more time actually. So even if I waited another 18 minutes, I think I wouldn't get the next tick. But what we got in the process was this image, and I think this is 2x2 generated images. So these are rubbish right now. I mean, they are nice color palettes actually, but they are just sort of 2x2 pixel images. So we don't see any shapes there yet. So if we trained this for long enough, we would start getting something like images from a real dataset. So there is a output of one network I was training for some time ago, and it saw 10,000 of thousands, so 10 million images, and I got to sort of, I was using the same trick, so bounding it with some area which padding it with zeros basically, and this is what the network was trained to sort of represent. So it's able to recreate images from some boat ride or something. This was again from a video, and it's just an illustration that you can sort of go and capture your own dataset with video. Actually, it's relatively easy to record a 30 minutes of something and then to train the model with it. So yeah, this is how this thing, how this what we are training here will actually end up being as well. It's just in a lot of time. Okay, so yeah, one more thing I wanted to add is that I added a bonus sort of part for this notebook. I will upload the latest version in our Git as well after the session, which is the details of resuming training of progressive GANs. So if you remember editing stuff in the config.py, if you, after that one liner that we changed, the demo time-lapse dataset, if you add these commands, train.resume id, resume snapshot, and resume k images, and basically add those lines here, let's copy it and paste it here, then it would try to resume from a folder which already exists. So it will try to find the first ID, and the ID is this 3 numbers. So it will try to open up the folder 000, and then it will try to find the network called network snapshot yeah, 009500. So this means this is some other model, of course, but it was trained on like 9 million images. And this number here is something that we have to set here with the resume k images as well. So it's a little bit, you have to do some like manual edits here, but if you don't change any of the other setup of this network, you can just sort of kill the Python train script, change this in your output, and then just restart it. And this is really handy because the network takes like forever to train, weeks or yeah, basically weeks. So if there is a hiccup on your on the PC side and something fails, or you have to restart, or you have to kill it for some time, this is really handy to be able to just stop it and play it again. And so we would restart this with some new network. It would create a new new folder. We can kill that again, and then we would just have to sort of update these values. So maybe change it to 1, change this to some like, maybe we will be able to train it for 100 thousands of images. So just change this as well, etc. Right? So these are the commands to sort of change that. Yeah, so they are not on our Git right now, but I will, after this session, I will save it with these outputs as well. So we will have that as well in the notes. Let's just continue with the next part with a notebook which we have in our Git repo as well. The third one, which talks about using a progressive GAN network, which has been already trained. So while this thing is something, while training is something that we cannot sort of do on a Google Colab instance or on a weaker PC, using those trained models for inference is something that we can do online with some speed, and also we can do it on our on a smaller machine as well. Or if the machine is really good, you can do inference in almost real time. So yeah, you might have seen some of my demos I was showing on the inaugural event of CCI, and I was basically using some trained progressive GAN models with some handlers or something on my side, so there was lots of stuff happening on that end. But basically, I was just like rendering frame by frame new images from that network. Okay, so let's see. What that means is that we will be sort of moving around in the latent space of the network. So we can imagine that the network has a sort of manifold in space, or I don't know, I think I called this a tablecloth in 300 or in 512 dimensions rather than in 3D, which is covering some space. And we know, or we maybe because this is a GAN, this is not an autoencoder, we found some places in that landscape which correspond to some faces, right? So we have found these to be maybe one property, and then this maybe to be another property, and we can do all sorts of types of edits on that. We can start maybe interpolating from one of these samples to another one. We can sort of start counting or calculating what would be the differences between some clusters, and then getting some what was the name of it? Is visual feature what was it? Visual attribute features or something like this. So we can sort of start adding the difference between two samples to a third sample and see what that does, and all sorts of that jazz, right? This is relatively complicated, so we will see it in some simpler demos in the third Colab. So in here, I will open it up, and I'm not sure what will happen if I'm running one at the same time. I think it might be slower a little bit, but let's see. I will kill it if need be. Okay, so a little bit of this code is similar like what we saw before, so especially the prepare libraries section, because we are just downloading the same repo again. So practically speaking, on your own PC, you wouldn't have to do this preparation step, right? Because you would already have everything. Okay, let's check the GPU. That's correct. Let's print out the version of TensorFlow, just to check if everything is okay, and then print out the NVIDIA SMI. debug. So let's see, Tesla P4. Okay, so they have different. Yeah, this is a smaller memory GPU than what we were given here as well. I think they noticed I'm using a lot of GPUs, so they scaled it down from Tesla K80, which had 12 gigs, into a Tesla P4, which has 8 gigs. Yeah, 12 to 8. Anyway, doesn't matter. We will not use it up all. Okay, so once again, I will go and authenticate. It will download a model. So this PKL file, which is something that we would be getting in this result folder. So after some time, after some iterations of this algorithm, some like maybe days, we will start getting, well, not days, maybe an hour or something. We would start getting these saved versions of the network. So these PKL files. We have downloaded a pre-trained model from the author of this paper, which is working with Colab A HQ dataset, which contains faces. If you look here, we can check all of the other models that they released. Yeah, let's generate maybe some cars as well. So in order to get the link, you would again copy the shared link, paste it here, and then I didn't remember what was the name of it. Let's replace this ID with this ID. Let's call this car because I forgot what the name is. Anyway, doesn't really matter. We will download this this model as well. And so when we print them all out, we can see maybe. I think it's slower because I'm running the other Colab as well. Yeah, so we will see that we have downloaded a car, PKL, and then Colab AHQ PKL. Okay, so let's still work with the faces one because that one has the higher resolution, and we will open it in this notebook. So we are loading that file and extracting the 3 networks that we saved in there. That is the generator, a discriminator, and something called the GS. If we print them out, we can see that all of them are networks. The GS is a generator which has been accumulated across a bunch of previous iterations of the network state. So basically what they did is that at every iteration they will save the generator, but also accumulate the average weights into a network called GS, sort of average generator. And I think they save like I don't know how many, some number of generators in that one. And what happens is that this GS generator is better at yeah, the quality of that generation is better because it sort of averages the small fluctuations which can happen with one iteration of the GS of the generator. So we will be using the GS. Okay, so let's actually finally use it. There are some helper functions. So generate latents to images or to image. So it will convert a array of latents. It will run it through the GS network, so this one. If I wanted to use the G network, I could change it here and see how worse the images are coming from a latest version of the generator versus the averaged one. And I am feeding it with the latents, some fake labels, and then it's generating me some images. The labels doesn't really matter in this case because we trained it without any data. And then this is a helper function which will just print out that image or one of those images as a plot. So let's call it here. We are generating a random vector of 512 numbers, then feeding that random vector through the network, and then getting the image. So this is some dude. If you run it again, there is another dude. If you run it again, another dude. Okay, there are some ladies there as well, I promise. It's the dataset of faces. So celeb AHQ, it's focused, or it has been trained on images of celebrities. So these images are not really real, not only because they are generated, but also because the dataset is somehow like artificial in some sense. But yeah, you can see that there are a bunch of faces which look reasonably well, and there are a bunch of faces which are sort of strangely, uncannily looking, because something's wrong with the network. Basically, there is some detail which is somehow missing from the image. Okay, well, so we are able to do this, and this process is us sort of just randomly finding a place in the dataset or in the latent space. So when we were looking here at this image, we are moving around this manifold of 512 dimensions. We are randomly selecting one place of this space, of this latent space, and just randomly saying, hey, okay, what's here? This face. What's here? This face. What's here? That face. Okay, what's here? This face. Well, so getting that, you can you can see that you can start playing around with that, right? You can generate a bunch of faces from this space. The important difference from the autoencoders models is that you cannot take a face of like my face or something, encode it, and then get the latent representation of that face. So you cannot really encode real samples there. What we are left with is really just randomly generating images. You can, of course, then like try clustering those images. So maybe you will find all images which belong to one class, and then all images which will belong to another class, just randomly through going through the space, or with some smart analysis, some like plugging in a model which will analyze your image here, and that would sort of allow you to look at this space and say, oh yeah, maybe this is a cluster which all the female faces are, and this is a cluster where all the male faces are, and then you could start getting some differences between these two clusters, and you can start sort of adding this difference to the individual vectors or to the individual points in the space. So I don't know if you can find smiling, not smiling, probably could, but there is a lot of smiling people. Okay, right. And so, oh yeah, this is a nice one. Let's end with the zombie. And so you can see that this is one way of sort of using this model. This is the simplest way of your just sort of asking it, okay, what's in this place of the network, very randomly. We can start interpolating between two places. So I wrote down some additional helper functions. So there is a interpolate vectors function, which will take a list of vectors, let's say 2, and then I want some amount of frames from it. So it will create a interpolation of 10 places in between those two vectors. This works also if you give it like 10 vectors and you ask it to generate 100 interpolations or 100 samples. So it will sort of ask for 10 samples between each pair of these, right? And yeah, there is some rounding somewhere, so it will sort of figure out on its own how to split those vectors if it's a weird division of those numbers. So we create a first latent here and then second latent here, so two random places in the space, and then I will tell this function to give me 10 places in the middle, and we will generate them. And yeah, this is just a side step this is just simple linear interpolation. So you could say something like lerp, linear interpolation, given a vector u, given a vector v, and then a real number a, I can just return a times u plus 1 minus a times v, and that will be my new vector. And so if I call this with these two latents, I think it should automatically work. And then let's say maybe have 0.5 here, and then call it dv. I can, yeah, let's just do it here. It will not only not fail, but I can also print print the first latent vector now directly, so I want to just see what they are, the second latent vector, and finally the V. And then if I look at them, well, it's hard to parse. Okay, so let's see the first maybe 10 numbers, 0 to 10. Okay, and so this first vector is this second vector is this, and the V is a linear interpolation between them two. So this is just a demo of showing what's happening somewhere in the background. It's this super simple function. I just made it slightly fancier because I wanted to have a be able to call and get like 10 intermediate vectors from there. But behind it, we are just using this thing. Okay. So let's get back to the inference part. So at this moment, we were sort of showing that we can linearly interpolate between two vectors. And so what that means is that we will just mix them together. And so if I will just print out the shapes, they will of course remain the same, right? Because I'm just saying, hey, give me a middle vector between these two vectors, and it will figure out the current one. I think I even had like a... yes. So what's happening is something like this demo of simple linear interpolation between two-dimensional vectors. This vector u is representing the first random latent I found. This vector v is representing the second random latent I found. And then this number in between is sort of interpolating between them. However, we don't only have like 2 dimensions as here, 2D. We have 512 numbers instead. So it's slightly more complicated, but as a visualization, this works as well. Okay. So with all of these, we can now take these latents that we generated here, that have the dimensionality of like, they have 10 saved vectors with 512 numbers, and we have interpolated these two numbers between these two vectors. We can generate the corresponding images from those latents. So let's run this. And as output, we will get 10, because that's how many latents we gave it, 10 images of 1000 by 1000 by 3. So 10 RGB images. And so there are different ways how to show all of this. There are helper functions to sort of concatenate images in horizontal or in vertical manner. So if I will just concatenate all of those 10 images and then show them, it will hopefully show me the images I generated. So this first one, this guy was the first thing that I generated with this one, first random vector, and this lady here was another sample that I generated with this random vector. And then this path in between is something that is generated along the path because of sort of just exploring the interpolation between two samples. Okay, so we can sort of do this in a larger scale. We can generate not just one line of these interpolations. We can generate sort of 2 lines or something, and yeah, like we can just repeat this process, right? So we would be getting from A to B, and then from A to B, and then we can repeat that again and again. So yeah, this is more or less for like debug purposes, just to show if the thing that we are seeing is working. Hey, let's see, this guy is without a smile and this one is with smile. So this interpolation actually is making that guy more or less like more smilier. So not just changing the identity, but also changing the this property of this generated image, which is interesting. One demo I wanted to show here as well is this visualization of bilinear interpolation, and I don't have it implemented there, but there is a question of sort of what are the ways of exploring that latent space, because just randomly sampling images from one here, and then seeing what's in the middle you are really exploring just one line inside that 512 dimensional space. So it's a very small area you are covering with this trajectory, right? Well, there is a thing called bilinear interpolation, where you can be you are interpolating from 4 or between 4 sampled vectors. So these are 4 vectors, and you are using 2 coordinates, one being the u, which is influencing sort of intermediate points on this scale between these 2 images and or these 2 vectors and these 2 vectors, and then another coordinate, which is the v here, which is showing you or getting an interpolation between these 2 resulting points. And so with this, you could, in theory, generate a full grid of images. So if I were to play it, you could sort of generate all the images that are on this spectrum using these 4 latents as inputs. So instead of just interpolating from one side to another, you could even have a grid of full-on interpolations between one sample here, one here, one here, one here, and then getting whatever the space is in the middle between these samples. So in the 512 dimensional space, imagine that we are sort of creating one line on one dimension, and then one line from the other dimensions, from other couple of points, and then from those 2 lines we are creating another sort of sampling on the space between. So as I would imagine it in 3D, it's a sort of ribbon shape that would be in 3D. But in 512D, we have no idea. Basically, you cannot make a ribbon in 512D that would be easy to understand. So it's a sort of attempt only to visualize more from that space. What I wanted to say with this metaphor a little bit is that interpolating or interacting with this latent space can be really tricky, because you don't really know in which direction to move. There is no real guidance between these dimensions. So moving in one dimension a little bit forward and backwards might make something and make something happen. It might also not do that. So like you don't have any control over that. And I think this is really a open research area right now these days to figure out how to control GANs to generate something we would be able to control. So yeah, that's a sort of a bigger picture message for you. Okay, let's get back to our simpler demo. We ended up generating a bunch of images, right? Yeah, I think let's find some nice ones. Let's have a nice trajectory in the second line. Yeah, let's say this is a good one. And let's generate. So sometimes the faces we generate are strange. So it might be interesting to go for the strange faces sometimes as well. And keep in mind that this is a dataset of faces. So if you are placing in anything else, you could be generating interpolations in any other domain, which could be your own curated dataset. So you could be sort of exploring space in between the samples that you gave it. So yeah, that's a really interesting area, because you could have trained it on your own creation and then explore what happens in between those samples. So yeah. Okay, let's go with this. Let's have a helper function here, and let's say that we want to save the second image or something. So this will be, because right now we are just debugging them out. We don't have them saved anywhere. They are still in memory of this virtual machine. So we can then save them. So save the second image, so this guy, and then show that test.png. And so this is the resolution of the guy or the image of that guy that we generated. So we can actually even print it out as a much higher resolution. Let's look at the third one or something. And yeah, I think this is now showing us much more details. So at this resolution or at this scaling, you can see that it's not perfect. If we show it at lower resolution, it will look better. And there are some tricks with super resolution GANs that can still fix it. And maybe if you find like a better sample, it might also look better than something on a trajectory between two samples. But yeah, some of these glitches happening in this space are something that is to be expected from these networks. Okay, so let's make a renders directory, and let's save all of those images that we had in that field. Then let's print out that folder, and let's see that we've saved 10 faces here. And so we can save them and zip them and download them in the usual way that we would normally do. Okay. Last sort of bonus is that there is I added a function which will convert a series of images into a video at some frame rate. So let's do that. This requires ffmpeg, I think, somewhere in the background. And let's just make video from these 10 images with a frame rate of 5 seconds. Okay, and let's look at that video file. It's 0.5 MB. So we can save the interpolation as a file of a video. So let's check it here. This one. It will allow us to save it, and then we can look at it. And it will be a bit choppy because I set it to 5 frames per second, but this is the trajectory that we generated, right? And so, I mean, using something similar and maybe using a larger amount of samples than just 10, and then a much nicer frame per second resolution here, you could generate a very smooth interpolation through that space. And I guess the sky is the limit here, because no one is forcing you to interpolate between one sample and another sample. You can sort of just play around with it and see, maybe save these interpolations and then move all of those images at the same time in some other direction, and so create grids which would be moving all around sort of together. Or yeah, just you can start playing around with this network. Yeah, I didn't add much more here, so I think we are near the end of us working with this model. I will finish this with just running the same thing over with cars, so that we see that this works with like another domain of data. And that is relatively easy to just load up another type of a loaded model and then start generating images from that area. Because faces to some degree are a bit boring. Hey, yeah, this is a car. Okay. Let's interpolate some things, and then let's look at the space between. We would do that here. Okay, so this is an inside of a car to the outside of a car. And let's generate some grids. So these are 256 by 256 resolution, so they are lower res images, but they contain different types of objects. And we don't have to end with cars, which are still relatively boring, I guess. Well, although this color merge is nice. You can look up at into the linked folder for pre-trained models, and there are all sorts of categories from the LSUN dataset, so images of airplanes, bedrooms, bicycle, birds, boats, bottles, bridges, buses, car, cats, etc., 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 etc. Right? So some of them will work nicely, some of them will not at all. But this is a nice resource to sort of find some weird models to play around before you can train your own. Okay. One thing I wanted to share with you guys is the code that I was working on at CCI. It's called GAN Explorer, and the purpose of this repository is to sort of play around with trained models of progressive GAN. So when you sort of finish with your own GAN, you can start with this repository to sort of help you out with interacting with that latent space. No, my images are dead. I had some visualizations there. Anyway, okay. Illustrations. So what this allows you to do is that you can sort of plug this in as a application where you are sort of controlling the latent space or navigating the latent space with just WSAD as if it was a game sort of. And then you can save those latents somewhere and then generate video interpolations and then maybe start hacking a little bit into that. So there is this effect which is changing the representation space with this strange effect, which is sort of messing around with what is represented inside. So you can sort of start breaking those representations even with other methods. And yeah, there is sort of endless ways to continue with what we started with today, and it sort of opens to your own research as well, or projects and yeah. Okay, so this was one last thing I wanted to show. And with that, I guess I will end with today's lesson. So for the next class, we will talk a little bit about sequential modeling. So the sort of last bit to the puzzle of current machine learning models. And yeah, we already saw this. And yeah, so this is basically the end for today's practical session.